Thank you for the introduction. So I would like to show you some results from our preclinical evaluation of an MR-guided thermal HIFU ablation strategy, or a histotripsy strategy as you like, in an in vivo porcine liver model. So the motivation for this project for us was that a disadvantage of MR-guided HIFU ablation in the abdomen is that we achieve in general a rather low ablation rate. And in a previous liver study in our institution, which was quite conservative because it was towards a treat and resect study, we achieved ablation rates of approximately 1.5 milliliters over 3 hours. And the main cause for this is that we have to wait for the near field to cool down in between successive sonications to prevent the type of skin burns that you can see here in one of our big model studies. So again, our goal was to increase the ablation rate without burning healthy tissues in the near field. And in doing so, we of course still want to be able to create confluent lesions. So we have to compensate for respiratory motion, but also we would like to be able to encompass some larger vessels in our ablation procedure. So what you see here in the images in the bottom is an NADH staining, where we performed an ablative sonication close to the vicinity of a vessel. And as you can see in the zoomed image is that the presence of these vessels has a strong effect on the local cellular viability. So currently for HIFU ablations, we use a sonication protocol at 1.2 megahertz ultrasonic frequency. We sonicate in ellipsoid-shaped cells of 4x4x8 cubic millimeters, and we then visit each cell in these clusters subsequently. We deliver 450 watts acoustic power until we reach a temperature for an ablation. This is illustrated in the bottom. So in the bottom left, we see a coronal view of the liver of the pig with the honeycomb pattern cluster. And in the right, you see the sagittal image with overlain in yellow the beam cone of our transducer. So our goal was to increase the ablation rate, or in other words, enhance the energy delivery. And there have already been quite a lot of methods suggested in literature how to do this. But we were particularly interested in, well, the methods that have been the topic of this session. So we would like to use nonlinear enhancement or shockwave heating. It's already been discussed quite in detail, so I'll skip over this slide. So these histotripsy methods, our main goal was to implement these with our current clinical equipment. So in our institution, we use the Philips Sonolab system, which is integrated in a 1.5 Tesla MR scanner. And to see if we could achieve nonlinear enhancement of the energy delivery, we compared a pulsed sonication protocol, the maximum acoustic power that we can give, to a control continuous wave protocol at energy equivalent. So in the pulse protocol, we use 1,000 acoustic watts at a 40 hertz PRF. We use 10 seconds of sonication time per treatment cell, which with our pulse length gave a total energy of 3.5 kilojoule. And then for the control experiment, we use 350 watts continuous for 10 seconds. With respect to the MR guidance that we use, well, of course we use the MR to plan our treatment cells and to evaluate our non-perfused volumes. Also we use the MR to monitor temperature, both in the treatment cell but also in the prefocal area. And in this particular set of experiments, we monitored in the prefocal muscle layer. Then we also, since we want to create confluent lesions, we use the MR for respiratory motion compensation. And this is done by placing a navigator on the diaphragm. And then we use a gating mechanism where we only sonicate after each exhalation phase. And this results in a total sonication duty cycle of approximately 65%. You can see this also in the images in the bottom. So here in the top left, you see where we could place our navigator on the diaphragm. And then this is an actual recorded displacement profile of the diaphragm over time. So as you can see, the displacement is quite constant because we have the animal under anesthesia. In the first set of our experiments, we wanted to validate that we could use the clinical equipment to enhance the heat deposition. So in our study, we have sonicated over 5 animals, and we used a total of 29 pulsed and 25 continuous wave sonications. And in between each sonication, we used a cool down time of 2.5 minutes. Now, since with our system it's quite challenging to achieve sufficient amounts of pressure to get this nonlinear energy enhancement, energy deposition enhancement, we used shot depths of approximately 3 to 4 centimeters measured from the skin surface. I have an example of a sonication. So this is what you will see here is an example of a 1000 watt pulsed sonication in the liver. As you can see, the temperature goes quite rapidly up to the ablative temperature of over 65 degrees Celsius. And then it cools down. So these are the results of the 29 sonications, both pulsed and control. In red you can see the pulsed sonications and in blue the control. And as you can see, for all 5 of these animals, we saw that when we use the pulsed high power protocol, we get both an increase in the energy uptake, but also the time it takes to reach the maximum temperature is decreased. And yeah, what's also noteworthy is that the graph of animal 4 in the bottom left is a bit more jaggy, but this is due to the fact that here we unfortunately had to use a lower sampling rate for the thermometry. So that explains why this one looks a bit more jagged. These are the results for the thermometry in the prefocal muscle layer. So in the top row we can see the 1 kilowatt pulsed sonications. And in the bottom row, we see the continuous wave sonications at low power. And what is most notable from this is that the curves look actually very similar. So there is no increase in the near field energy deposition when we use the high power sonication. Now in our second set of experiments, we wanted to see if we could increase the ablation rate without damaging the healthy tissues in the near field. So in the last 3 of our animal models, we used a total of 48 pulsed sonications at high power, and we used a cool down time between sonications of only 40 seconds. So we really wanted to investigate how high we could go with the ablation rate. Again, we used shot depths between 3 and 4 centimeters from the skin, and for these ablation cells, the total treatment time was between half an hour, 45 minutes. So in the bottom left, you can see that we extended the honeycomb cluster here by 5 cells. So in this, this was the way in which we extended the cluster. So we just increased the circle. And these are results of our second set of experiments. So in the table on top, you can see that indeed we used the treatment times of 30 to 45 minutes. And the non-perfused volumes that we obtained were in the order of 2 to 3 milliliters. And this resulted in an ablation rate of approximately 4 milliliters per hour. And then after these sonications, of course, we turn over the pig to see if we can detect any skin burns. So in the top right, you see just a reminder of what these skin burns used to look like. But in our case, in this particular case, which was the one with 22 pulsed sonications with 40-second cooldown time, we had no visible indications of skin damage on the pig's belly. We then proceeded to dissection to evaluate our lesions. So as you can see, this is an exemplary lesion, again with a total treatment time of 30-45 minutes. And we were able to ablate a large confluent lesion in the liver. Now, the second research question that we had was whether we could encompass the presence of large vessels. This still remains disputable because in one In a couple of cases, we still had this strong effect of the local perfusion, but also in other cases, the vessel was completely ablated along with the target. And we hypothesized that this is due to the amount of pressure that we achieve in the focus. So actually, when we do have a sufficient amount of pressure, we believe that we can get a confluent ablation. We then used our NADH staining to classify the type of lesion that we did with this sonication protocol based on prior art. And we believe that we can classify this lesion, which has been called in literature as a vacuolated thermal. So, and this was also in agreement with our H&E staining, where we look at the tissue structure. So in conclusion, our pulsed high-power sonication protocol was successful in ablating confluent lesions under MR guidance with our current clinical equipment. And application of this protocol enhanced the energy uptake compared to an energy equivalent continuous wave protocol, which we demonstrated using MR thermometry. Now, potentially, we can use this high-power pulsed protocol to achieve an ablation rate of 4 milliliters per hour without causing any undesired damage to the near-field tissues. And again, we hypothesize that if we have a sufficiently high pressure, then we can overcome the heat sink effect caused by large vessels to create confluent lesions. Finally, I would like to mention that, of course, the nonlinear acoustic phenomena are quite complex in nature. And so in future work, we will focus on treatment monitoring so that we can apply these techniques in clinical practice. I would like to acknowledge the following people and thank you for your attention.
Very well done.